Okay. The main aims for this presentation is to give you a clear definition of what is metabolomics, and especially nutritional metabolomics. And later we will see what are the main steps in the metabolomic pipeline of a study design. And finally, I will show you 3 examples of applications in recent metabolomic studies. So let's go with the definition about nutritional metabolomics. In a very simple way and simple words, we can say that metabolomics is the omic discipline that tries to study how the diet influences our metabolism. Okay, this is the definition of the Metabolomic Society, which defines this science as the study of the dynamic, multi-parametrical metabolic response of a living organism to a pathophysiological stimuli, an environmental change, or a genetic modification. From this definition, I want to point out 3 words. Dynamic, because our metabolome is constantly changing, and this is something that we want to learn more. I mean, we don't want to study metabolites at a certain time, but during a process, during a whole study. As you know, our metabolism depends on many parameters. We will have a look at that later in the next slide. And then when this response is due to an environmental change, due to a change in the diet, that can be changing our dietary habits because we are changing the some macronutrients or micronutrients intakes, or we are adding a functional food to our diet, or we want to see the effect of a bioactive compound in a specific food, then is when we are talking about nutritional metabolomics. So, as I have previously mentioned, our metabolism depends on several factors. Which can be divided in intrinsic factors and extrinsic factors. Intrinsic factors are like, well, our age, our health status, genotype, tissue turnover, but I'm more interested in the intrinsic factors, which are the ones that we can change. And we can change the content in our diet of nutrients, of non-nutrients. We can change our physical activity. We can work also on the colonic microflora, and well, other points that I will talk later as well. And at this stage, I want to point out that metabolomics is about small molecules. That means that we are not looking for big macromolecules or big proteins or hormones, but we are interested in metabolites, both endogenous and exogenous metabolites of low molecular weight that are present in any biological system that we are studying. In our case, the human organism. Okay, and the main aim is to profile all these metabolites present in the sample that we have chosen to improve the understanding of the effect of this particular stimulus, in our case, of the effect of any nutritional intervention on the metabolomic pathways, to understand the healthy effects of this biological change due to nutrition. Okay, and most of you are nutritionists, I think, and you must be thinking why it's important for you to work in metabolomics or to have this tool in your research life. And this is basically because it's a very nice way to look for biomarkers, but not traditional biomarkers that as we are used, like for example, you are used to look for levels of triglycerides, levels of cholesterol, LDL, LDL, but only focusing in one metabolite mainly. But in metabolomics, what we look is for metabolic profiles. It's like a whole set of metabolites that you can analyze at a certain time and only with an analysis, and it gives you an overview, a whole picture of the situation of the health changes in that moment in the metabolism of our organism. And you can look for biomarkers of intake, which are quite useful for dietitians and clinical doctors in their studies when they want to get objective dietary intake assessment of what the patients are eating, to know if the patient is really following the diet or not. There are some groups of populations that's a bit difficult to be sure if they are really doing what you are asking them to do, or they are reporting their consumption, like for example obese people or children that they cannot provide complete questionnaires, or elderly people. So it can be useful if we can have a biomarker, a profile, a metabolic profile of what they are really eating without questionnaires or any other tool. And then we are also interested in biomarkers of the effect of nutritional intervention of human health. For example, biotechnologists must be interested in seeing if a new formulation of a functional food is really working into the antioxidant capacity of the body. And then finally, we look also for biomarkers of early disease. This can be shown clearly in the following slide, because you have to remember that metabolites are the cellular endpoints of gene expression and of any physiological regulatory process. So in this graph, what is shown is the change over the time of a profile of metabolic biomarkers from the state of healthy, from the state of homeostasis to the state of disease. And we are interested in studying biomarkers, in finding biomarkers in this area. Why? Because it's the moment in which the homeostasis is lost, and it's still, there are still not clinical alterations, and it is not too late to try to solve the problem, to try to avoid the disease, and maybe with an early intervention, changing diets, physical activity, and all other tools, maybe we can prevent the onset of the disease and avoid the pharmacological treatment. Of course, this is very how you say, well, it's very, I mean, it's not the reality, but yeah, idealistic, that was, thank you. And, but well, this is the main goal of metabolomics in looking for biomarkers of early disease. So, when applying metabolomics in nutrition, it's quite a complex thing because there are many factors playing a role, and we are of course looking for very subtle differences, because the diet is one factor among lots of others in our body. And this is a very nice picture that shows very simply what are these interactions between food and our organism. So on the left hand we have the human metabolome, which can be divided as endogenous metabolome, and the exogenous metabolome, which is divided in the food metabolome, which comes directly from the foods that we are eating. Also the microbial metabolome, which is called microbiome, and it's very interesting to look deeper in the future, in future studies. And then also we cannot forget the xenometabolome, due to the drugs and toxins that are also interacting in our body. And on the other side we have the foods, but we have to keep in mind that the metabolites that are in the foods are not the ones that we will find in our metabolome, in our body, as they are in the foods, because the process of ingestion, digestion, the chemical transformations only by effects of cooking are changing a lot our these metabolites, and that's why we need of techniques to first to identify which are these transformations, and then to see the effect in our body and our health. So I hope that the definition was kind of clear, and now we're going to move to the steps of the Metabolomic pipeline, which are mainly, and before that, we have to keep in mind that a metabolomics study needs of a careful study design, basically because, as you can imagine, there is a very huge inter-subject biochemical variation that has to keep in mind in the design. And just to reduce this variability, we usually conduct carefully controlled dietary interventions with the double crossover study design because every subject is its own control. So it's easy for us to link samples. And then, of course, we need a sufficient number of individuals per grouping, basically because we need robust statistical models, and as always, the more the merrier, the more individuals we have, the better. But you know that these kind of studies are not cheap, and so it's kind of have to get to a balance just to get the statistical significance. And then, of course, we have to decide the criteria of the selection of participants. In some cases, we will be interested in a specific range of age, or only in men than women, and so on. So this has to be kept in mind before performing the study. And this is the pipeline of the study, and we will go briefly through all the steps, which are sampling, data acquisition, data pre-processing and processing, and metabolite identification, and final biological interpretation of the results. So let's begin with the sampling step. And once you have recruited your subjects, you have your hypothesis to test, you carry your nutritional intervention, so many weeks as you have fixed, and so on. You are collecting samples every now and then in your study. Basically, baseline endpoint, but the more you get also during the study, the better as well. And the main samples that are usually studied are biological fluids, and we have blood plasma and blood serum or urine. But nowadays we are also moving to the study of tissues, of cell extracts, saliva, fecal waters. So it's a broader word to work in metabolomics. But the main studies are still being done in blood and urine. And blood gives us more idea of the changes in endogenous metabolites, reflecting of this impact of the effect of our intervention. While urine is more related to the exogenous components of the diet that are, of course, metabolized by our human tract while coming from through the body. And then we have to also to decide if we want to take the samples in a non-fasting state or a fasting state. And this, of course, depends also of the design of your study. For example, sometimes you want to perform postprandial studies to check the bioavailability of an active compound, and then you need to take samples at different hours, so it's good to have fasting samples. But in a normal human intervention that lasts, let's say, 4 months, then it's maybe better to keep full records of the diet that you are that your patients are following, and get fasting samples to correlate your results, your data. And urine also, it depends. You can have spot morning samples, 8-hour samples, 24-hour samples. It's also depending on the application you want to have. Okay, and the sample preparation is very simple, and of course it has to be optimized, but it's something that has been done for a couple of years for groups that are involved on that. And basically, when treating with plasma, we needed the proteinization and a solvent extraction. And in urine is very simple because most of the time it's only filtration and setting the pH, and the sample preparation is quite easy. But it has to be carefully done, of course, as every step in the methodology. Then once you have the sample, next step is to inject it in the instrument, in your equipment, and to get data for your study. And there are two different approaches, technical approaches, that they are targeted or non-targeted metabolite profiling. The first one consists in analyzing a group of metabolites that are related to a specific compound or a specific metabolic pathway that you want to study, and it's very useful for getting quantitative measures. But the most common and let's say most challenging approach is the not targeted metabolite profiling, because it's a non-hypothesis driving approach, and there you really don't know what are the metabolites that will be important for your study, and it's a question of comparing different patterns, and that they are called fingerprints, because each group of subjects can have a different fingerprint. Okay, and the methodology, the techniques that are mainly used are NMR or MS. MS can be coupled to a previous chromatographic separation like GC or HPLC, but also there are direct flow injection methods that don't require of this chromatographic separation, but the data to treat is more tricky and difficult. I'm not going to go in this talk into detail of the techniques, but if you are interested, you can always ask me for any review or so, and I will gladly give it to you. But just to show you that since metabolomics began to be applied in nutrition, which is not so long time ago, the main technique that has been used is NMR, taking into account that these are the papers that have been published in the field. But lately, MS fingerprint is really going up. But the trend nowadays is not to work only with NMR or MS, but to combine both platforms. And why to combine platforms? Because to get to know all the metabolites of our organism is not an easy task, and the more techniques that we use, the more metabolites we will be able to identify. But of course, these equipments are really expensive, and not every group can afford all of them. But the good thing of metabolomics is that it's a multidisciplinary approach, and of course, not one group cannot do the whole pipeline steps. That's why we need collaboration from the beginning, from the medical doctors and nutritionists that are designing the study. Then we need analytical chemists to perform all the analytical measurements. Then we will need bioinformaticians to clean our data. And finally, we will need also biomolecular or biologists to help us to interpret what have been the results. So it's nice to see that this is a technique that brings many people from different disciplines to work together. So, once you inject your sample in the instrument, what you get is a large set of variables. In the case of MS, corresponding to detected ions, and in the case of NMR, of chemical signals. And these variables, each of the variable is defined by the retention time, the exact mass and charge, and the intensity of the ion. And what you get is a really long list of these variables that if lucky, once you have cleaned all the data, 1 or 2% of these ions will be a real marker for your study. So we really need a great help of bioinformaticians to help with all the data cleaning. Then after the collection of the data, we have to analyze it, and of course we need of a pre-processing step, which englobes different steps, like filtering noise. Like, for example, in LC-MS, you have, of course, the retention time of your metabolites is changing depending on many conditions: the temperature of the column, the amount of samples that you are injecting per day, the batches that you are designing in your study. So there are many factors that make these shifts in the chromatograms, and before you can compare them, you have to align them, and this is done by mathematics algorithms. And this is what is called data mining, and englobes all these data pre-processing steps that are needed so that you can go into the statistical analysis. For this, we use different softwares. There are commercial softwares, free softwares. There are some that are very user-friendly, some others not that much. You need to have experience in R languages and Java languages, that depends. But there are many options, and you just have to see which is the one that it fits to your study. And after this processing of your data, what you have is a list of possible biomarkers that are significant different, and you have two options of studying them. They can be done by unsupervised methods without knowing previously the classification of your samples. And the most common one, as I think that most of you know, is the principal component analysis. I will talk a bit about it later. And then there are supervised methods that need of very careful validation to avoid overfitting of the data. And this is one of the examples of the technique. Let's just see the most simple one, which is the PCA. And the PCA, it gives you different components that what they do is to reduce the dimensionality of the large data that you got by building these components that describe the maximal variance of your data. Here I put an example that PCA analysis, what it brings to you is a score plot where it is shown the classification, the separation of the samples according to each group of intervention, if you are lucky. Sometimes if you don't see already here the difference, then something has been wrong in previous steps. You have to check again your data and so. And if lucky and you see already a separation, then you go to the loading plot, which shows you a clue of possible metabolites. Well, not metabolites, but they are metabolites. But what it shows you in this case are the mass, the exact mass of this ion that is causing this separation of samples. Okay. And the next step is the metabolite identification. Once you have this set of metabolites that have become significantly different among the intervention groups, you just have to identify them. And the tools that are usually used are elemental composition tools. If you are working with high sensitivity mass instruments, also you can use data. You can see if the metabolite is in open database. I usually use Human Metabolome database, which has thousands of metabolites in the human body, but it's still, it's a very good database, but of course not everything has been found out. And in the case that your metabolite is not there, you have to perform tandem MS and to see the mass fragmentation pattern of your ions, of the ions that are more intense, and if lucky, with the fragmentation pattern, you will have a clue of what kind of family and compound you are working with, and if there is not a standards, you will end up asking for organic synthesis of that compound if you really want to corroborate the identification of the metabolite. But according to the experts, no more than 10% of the ions that are observed by high-resolution techniques can be identified today in open metabolite libraries. So that's still a long way and hard work to get metabolites identified. I must say that this step of the metabolic pipeline is maybe the more time-consuming, but if we after all the work done, if we don't identify the metabolite, there is no point to go on with a study. So it is worth it to work on this. And this is an example of how Human Metabolome database works, and you can use different modes, well, it's depending on the mass spectrometry data that you have. And just as an example, I wanted to show you that, in an instrument that you got 4 decimals sensitivity, you have really quite many options of very similar compounds that can be in your sample. So it's not a trivial thing to identify metabolites. Okay, and finally, once you are lucky and you have identified, of course, maybe not all of them that are significantly different in your study, but some of them, then you can go to the biological interpretation, if lucky, and you get to the end of this pipeline. And what you will do is to try to look for the known pathways that we know and see where does this metabolite fits, and together with the hypothesis that you had at the beginning of your study, you will be able to explain why this metabolite is increasing or disappearing in this pathway. But as always, it's still very difficult to interpret these changes in concentration in a given context. But that's why we need of molecular biologists to help us, and medical doctors and pharmacists to help us with the interpretation. So, and finally, I will show you 3 examples of applications of case studies. And the first one is a very typical study in metabolomics, and the aim is to look for subtle metabolic changes in similar foods. And in this case, they chose to compare the effects of black tea and green tea on human metabolism. And this study was performed with 17 healthy men, and in a crossover study design. And people was given 1 gram of tea solids per day, and as a control group they used the same amount of caffeine that is in this tea, And they collected 24-hour urine and plasma samples, fasting samples, and they analyzed the data with, the samples with NMR. And they got, this is the example that I showed you with the PCA, they applied PCA, and they got separation of the control and of both these T groups interventions, and they found changes in exogenous metabolites, and they show increases in hypuric acid and 1,3-dihydroxyphenyl 2-sulfate, that both of them are two end products of flavonoid metabolism by colonic microflora bacteria, and in both these, in comparison to the control group. And also there were there were like 5 aromatic metabolites that were detected in urine, but specifically after the intake of green tea, but not after the intake of black tea. So these biomarkers could be used as intake biomarkers of green tea. But at that moment, this paper is from 2006. At that moment, they were not able to identify these metabolites. At least they knew that they were there and that they are different from the black tea after black tea ingestion, but at the moment we don't know what kind of metabolites they were. And I've looked if I could find some more papers of this same group to see if they have gone farther with that, but I was not lucky with the search. And then, apart from changes in exogenous metabolites, they also found changes in endogenous metabolites. And the green tea intake caused a stronger increase in urinary excretion of several metabolites from the TCA cycle, like pyruvate, oxalacetate, and citrate. And this made the author think that specific green tea flavonoids have something to do with the human oxidative energy in human metabolism. Okay, and a second example, it's about showing the influence of a long-term diet in our metabolome. And this is from this year, from 2010, and it's a nice study that shows how can we distinguish lacto-vegetarian subjects from omnivorous subjects only by analyzing 24-hour urine samples by NMR. And the subjects were, the lacto-vegetarian subjects were subjects from a Buddhist community, and they were enrolled in this community for more than 5 years, so it's a long-term period that they have been strict lacto-vegetarians. And this is very nice because as they were having lunch and meals in a communal kitchen, it's a perfect situation to control all the food variables of a study. And as omnivores, they took just as normal people of China. And here you can see that the PCA scores that for males and for females, because this study was also had a second objective to see if there are also differences in the gender in lacto-vegetarians and omnivores, but I'm not going to go into this point. And but you see that for both males and females there was a very clear division of vegetarians and omnivores, and the loading plots give them very nice clues of metabolites responsible of this division. And here you have the main metabolites that were changing and were responsible of this classification, and among them, for example, point out the amino acid taurine, that it's an amino acid that is found mainly in foods of animal origin. And of course, it was decreased in the lacto-vegetarians. This is increase or decrease of vegetarians versus non-vegetarian. And of course, if you want your subjects, vegetarian subject, to increase, to have correct levels of amino acids, then you have to another options to look for other options like algae or fungi to increase taurine levels. And also, the hypo rate was increased in lacto-vegetarians, and this is due to the fact that this metabolite is indicative of plant-based dietary habits. Also, there were some other specific metabolites present in meat. And nicely, for example, the citrate was increased in lacto-vegetarians. Why? Because its urinary excretion is strongly associated, influenced by the acid-base status of our organism. And eating meat, let's say that, in simple words, let's say that it has an acidifying effect because of the content of specific amino acids. And eating more fruits and vegetables, it gives you an alkaloid load. And this was very nicely correlated with the urinary excretion of citrate. Okay, and as the last example, we will see how dietary preferences can also influence our metabolism and our microbiome. And this is a study that was performed by Nestle last year, and the aim was to monitor metabolic changes associated with the daily intake of a choco bar of 40 grams of dark chocolate. I think it was more than 70% of pure chocolate over a period of 2 weeks in urine and plasma subjects of 30 subjects that were classified according to their anxiety trait. So psychological factors are also, it seems that could influence in our dietary preference and in our metabolism. Let's see if this is what they found out. What they did was to divide the participants into high or low anxiety trait by making them to fill in a psychological questionnaire that is used in this field and it's already validated. And they had also a week of washout without chocolate. And the samples were taken at the beginning and at the end of the intervention study and also in the middle of the study. And this is an example of a very nice application of NMR, GCMS, LCMS, and then the statistical test. And what did they got? Okay, at the baseline and time zero, they already noticed a classification, a difference in the metabolism of those subjects that reported to have low stress versus the one who have high stress. And the main changes were in hormonal metabolism. And the people with high stress, they have higher urinary excretion of adrenaline, dopa, and 3-methoxytyrosine, that they are well-known two intermediates of the dopamine synthesis. And this implies a greater synthesis of catecholamines in high anxiety subjects. So from the very beginning, it seems that there are differences in our metabolism because of our psychological traits. And at the end of the study, after having the 2 weeks of eating one chocolate bar for 2 weeks, the levels of catecholamines, of corticosterone and cortisol, were reduced in the urine of these subjects with high stress. In the case of the subjects with low anxiety, there were no changes in these metabolites. So that's kind of a good result that they got, that eating chocolate moderately, one bar per day, helps the high anxiety people to reduce their levels of stress hormones and so on. This was found. And also there were also changes in microflora metabolites that were varied only in the people from high anxiety, suffering of high anxiety, and these levels of these metabolites tend to be normalized to the levels of the people without anxiety. So it seems that chocolate can work for high anxiety people. And I think that with this slide, I finish my presentation by thanking you for your attention.